Hi, everyone. Mr. Neighbor here, and we're going to be talking about the very last section of Chapter 13, 13.4, Conservation of Energy. Energy is something that has always been there. It can neither be created or destroyed. It only can be conserved. So the sum of all energy is always going to be zero. The change in energy in the universe cannot exist. So all energy has to be converted to other things. So the sum of all changing energy is zero. It's always going to be the same amount. You might have potential energy, a certain amount, and you might have kinetic energy with a certain amount. And that's going to equal those two things in the end, but there might be different quantities. Remember, there's a lot of different types of potential energy and a lot of different types of kinetic energy out there. So there's not going to be the same amount of potential or type of potential energy in the end, but the sum of all energy, that will be the same, not going to change. A great way to think about energy being conserved is with a roller coaster. Roller coasters have a lot of potential energy when we're looking at the top. Here, if the cart is completely still, there's no kinetic energy and there's only potential, no kinetic. But then as we get down here, notice we're only a little off the ground. So our potential energy is now very, very tiny. But that other potential energy that we had is being converted into the kinetic energy. So you can see that kinetic energy and potential energy are still going to be equal to this only potential energy over here. So we'll do examples like that and move on from there. But before we look at that, we want to make sure you know something about systems. So, a system is a portion of the physical universe chosen for analysis, for you to look at when problem solving. Everything else outside of the system is known as the environment. The environment is essentially ignored except for its effects on the system. So, a lot of times when we talk about momentum being conserved and things like that, we're talking about a specific system. And then everything outside this system, we don't necessarily talk about. So, inside of a system, you might notice that energy is not conserved. But in the bigger environment, the universe, energy will be conserved. But in a specific environment, or sorry, in a specific system, it might not be if the system's too tiny. So just know energy will always be conserved in the universe. But if your system is too small, it may not be. And that's okay. Just to recognize that that's okay is what we're going for. So when looking at some systems, there are isolated systems that are unaffected by outside influence, and there's non-isolated systems where you have work being done on it or thermal energy being lost in it. So, for example, this girl on the swing with or just herself, if she is the system, her brother is the thing that is exerting the force, and he is outside the system. So this would be an example of a non-isolated system because her energy, if she's still right now, would be one quantity. But as soon as the brother pushes her, he made work happen on his sister and or the little girl, and that added energy to the system. Now she has more energy than when she started with. So it would seem that energy is not conserved. That's only because our system is so tiny. If you have an outside or an isolated system, sometimes you want that to be true for experiments so you don't have anything else affecting it. You enclose things so well that no heat loss is possible, no force can be added to it. It's only those forces that are there. It's isolated, unaffected by any outside influence. So typically, we deal with a lot of non-isolated systems. So to clarify a little bit more, because systems are important, if I was looking at a falling ball hitting the ground with only the ball as my system, energy would not be conserved because the movement, kinetic energy, disappeared and didn't transform into another energy affecting the ball. When it hits the ground, and let's say it doesn't bounce at all, it just stops like a bowling ball. It went from kinetic and the kinetic just disappeared. It did go somewhere. It went out as heat and as sound energy. But for that system, the ball, it wasn't conserved. If I'm looking at a falling ball hitting the ground with the ball and the ground and the surrounding air as my system, energy would be conserved because the movement kinetic energy from the ball is being transformed into sound kinetic energy and thermal kinetic and potential energies. So make sure you're thinking about systems when thinking about energy. So we said that there's only two types of energy. The two types are potential and kinetic, which all have subcategories. Mechanical energy takes two specific subcategories together. Mechanical energy is a term that we use to refer to gravitational potential energy and movement kinetic energy. So those two energies are the ones we're going to be focusing most on. That's what we're going to be talking about when conserving energy. Okay, a car on a roller coaster has 1,500 joules of potential energy at the top of a hill. How much potential energy does it have halfway down the hill? At the bottom. What about kinetic energy? Assume all energy is conserved with no friction. So we're not losing any energy to heat. Okay, so if I write ME, please don't confuse that with mechanical efficiency. We're talking about mechanical energy right now. So if I'm looking at a roller coaster, when it's at the top of the hill, it has 1,500 joules of potential. Let's say that it doesn't have any kinetic energy at this time. It's at the top. So now halfway. That means the distance, the height has been halved. So that means the potential energy is going to be halved as well. So now it's only going to be 750. That was a little hard for me. So where did the other energy go? It has to go into the kinetic energy. So now this roller coaster has some speed to it. When it's at the bottom, that means there is no height anymore. So there is 0 joules of energy. So where did that remaining 750 go? It went into the kinetic energy now. So see how the energy was transferred throughout the process. Object which weighs 1.02 kilograms is dropped from rest from a height of 4 meters above the ground. When it has free fallen 1 meter, how much kinetic energy has been gained? So let's look at the mechanical energy before and after. So gravitational potential energy before, kinetic energy due to motion before, and then after. And actually, let's just change colors here for after. What you probably should do for before and after situations, you can write an after up above, you can, and then a before above. Sometimes what I do I'll put a little I after this with a comma. So I know it's the initial, and then do the same thing over here, comma, I, comma, comma F for final, comma F for final. All right, so potential energy before. I will take the mass times the acceleration due to gravity times the height. There is no movement, so there is 0 kinetic energy, so I don't even need to write that. So I have 40.8 joules of potential energy here. So that's all the energy, 40.8 joules of energy, period, in that system before. That has to be the same amount after. Now the potential energy after, calculated the exact same way, but it's fallen 1 meter, so now we're 3 meters off the ground, which means that energy went somewhere. So I do have kinetic energy, so I set up the formula, and then I'll have to solve for V squared, or sorry, just for V. I'll subtract this energy, 30.6 joules, over to the other side, divide by 0.51, and square root both sides. Get out 4 meters per second.